This is the packet. When we're on campus, there are all kinds of group activities, Desmos activities, and whatnot. Typically, I give a brief lecture on the topic and then assign some pages from the packet for people to work on as a group. And then I go around helping people with it. I still strongly encourage people to form study groups because in this class, people are at all different levels, and I think it's very helpful for a lot of people. It's how the course was designed. But even though we're not together, I'm going to use this packet to guide what we do. We never get to all the activities in person, so it's not the end of the world for us to have to skip a few. I might put some of the Desmos activities up so people can see what they look like. But anyway, let's start on page 19. Now, this activity is all about getting people into ALEX and making them aware of the textbook that's in ALEX. If we go there, hopefully your view looks something like this, and the textbook is up here. It might take a minute to load. But this is what the book looks like, and you can navigate with these buttons up here. But I'm not going to read the book to you. If you want, this would be a good time to pause the video and try this exercise yourself. Let's establish some of the vocabulary. A relation in X and Y is a set of ordered pairs X, Y. The set of first components, that is the X components, is called the domain, and the set of second components, or the Y components, is called the range. So the domain is everything that X can equal. The range is everything that Y can equal. Eventually, you'll see a graph that looks something like this. Arrows. And they'll ask for the domain and range. Well, the domain is everything that X can be. And remember, X is the horizontal axis. So this graph is showing that X can be anything. The domain here would be negative infinity to infinity. But Y will never go below 0, right? You see the graph of this sort of stops at 0 down here. So the range is everything that Y can be, and in this case, it's going to be 0 to infinity. And this thing goes right down to 0 here. Some notation to keep in mind. When I use the square bracket, it means that the interval includes the point. So if you have 2 points, this one's not included, this one's included. So like 1, 2 would start at 1 and end at 2. But 1, 2 would start just after 1. It wouldn't include 1, and it would include 2. Okay, now here's an important definition. We'll be dealing with functions for this whole class. If we have a relation, which is a set of ordered pairs X and Y, that relation is a function if and only if for each element Y in the range, there exists exactly one X in the domain. So Y is a function of x if there's exactly one value of y in the range. If a vertical line intersects the graph of a relation in more than one point, the relation is not a function. What this means is that 2x can go to the same y, but 2y can't come from the same x. Each input can only have one output. And one way to see this is by graphing and checking with the vertical line test. The vertical line test says that y equals f of x is not a function if you can draw a vertical line through 2 points on the graph. So if I have a graph that looks kind of like this, then that's not going to be a function. Hopefully, you're familiar with the graph y equals x squared. Let me get rid of this. I'm going to graph this x, y. So if x is -3, y is 9, because -3 times -3 is positive 9. If x is -1, y is 1. If x is 0, y is 0. X is 1, y is 1. If x is 3, y is 9. And you're going to have a graph like I just drew that looks like that. Is that a function? Yes, because we're allowed to have 2x going to the same y, which is what you see there. But there's no point on this graph where you can draw a vertical line and have it go through 2 points. See, it's always going to go through the 1. On the other hand, let's say that y is the positive or negative square root of x. So I'll write up here. So y equals plus or minus square root x. So in that case, it's kind of the opposite thing, right? You have x, y. So when x is 9, y can be -3. When x is 1, y can be -1. X can also be 1 and have y be 1. And x can be 9 and have y be 3. And then the graph is going to look like this. And is that a function? No, because now we can draw the vertical line through it. So when we think of y as a function of x, we can think of y equals f of x. So in function notation, something like this would just be f of x equals 2x plus 1. Given a function defined by y equals f of x, this would be the set of all x that produce a real number when substituted into the function is called the domain of the function. And this would be the set of all y. When we graph a function like y equals g of x, when they ask you find g of 4, what you need to do is substitute 4 for x. So what this is asking you is, what does y equal? What's the y coordinate when x equals 4? And you can check on the graph that when x equals 4, y equals g of 4 equals 1. Similarly, when they ask you for what values of x is g of x equal 3, well, y is g of x, so we look for where does y equal 3? Well, that's x equals 2. And it doesn't look like there are any others. When we have a function of two variables, we sometimes would like to use one to predict or explain the other. In this situation, there is a dependent variable and an independent variable. The independent variable will be x, and then y is some function of x. y depends on x, so y is the dependent variable. When you're trying to solve word problems regarding independent and dependent variables, it helps to think of which is more likely to cause the other. For example, if you increase the number of people who are going to the movie, that would cause the price to go up, whereas increasing the total cost of the tickets does not cause more people to show up. So the number of people is the independent variable, and the dependent variable is the total cost of the ticket.